We're doing math. We're doing math. We're doing math. We need to do math quickly because my dog is hungry. We're doing math. We're doing math. All right, let's do some math. Let me try to not die as I don't get tangled in cables while I get back to my normal recording position away from the musical keyboard and toward the typing one. Okay, I think this is a success. I think we did it. Let's do some math. Here is my first mathematical volley to lob at you. Just going to let you think about this for a moment. I hope you feel uncomfortable. Just in case the singing didn't do that. Okay, let's talk about multiple integrals, the actual topic of the day. And quickly, because my dog is hungry. With multiple integrals, so when we're integrating over two or more variables, then similarly to partial derivatives, there is going to be a flexibility in the order of integration, usually mostly. So if we have a nice function that isn't doing really weird stuff, which they do exist, but for most functions, and I think all functions we're going to deal with in this class, you can change the order of integration, which is great. You can integrate x and then y, or y and then x, or, so on. When you do this, however, there is something really important to keep track of because it is the difference between wrong answers and right answers. You have to be careful of the bounds of integration. If you're doing definite integrals. If you're doing indefinite integrals, then whatever. But if you're doing definite integrals, then you need to do the bookkeeping correctly. And the way that this is done is your variables go from the inside of the integral toward the outside. So C and F here, these bounds on the inside, they go with the inside variable. So those are our x bounds. And then our y bounds are the ones in the middle, B and E. Our z bounds are the ones on the outside, A and D. And when you actually are executing this integration, the idea is that you're integrating f dx from C to F, and then you take that result, you integrate it over y from B to E, and then you take that result and then you integrate it from A to D over the z variable. All right, that's what I just said. As long as you keep track of your bounds of integration, you can change the order, especially if you think it's going to make the problem easier to do. Also, when we're dealing with multiple variables, remember that integrals have units, and the unit is the product of all of the stuff inside the integral. The d variables, they don't have to be spatial variables. You can integrate over lots of different things besides just coordinates, and also the units of the function itself, the integrand. Like, to give a non-coordinate example, if we're going to integrate a current density, so that integral, that integrand, the current density, has units of amps per square meter. And if we integrate that over an area, then the dx dy will have units of area, which will cancel the square meters in the integrand. And then we end up with a total current that is going through some area. And I chose this example because I really want to think about these integrals very physically and not just as sort of abstract calculations. Having said that, we're going to start abstract and then get to the physics. So here's just like a straight up math problem. Hello, look at me. I am an abstract math problem. Do an integral. So just to show the steps of how this works out in practice, we put in our function, we write our bounds of integration. Now, looking at the coordinate plane, what's happening here? So here's our x, here's our y. We are going to be integrating over some area from which I already drew incorrectly. Good work, me. Try that again. Okay, we are going to be integrating over an area that goes from 0, 1 to 1, 2, 3, 2. So this rectangle here, this is the area that we are integrating over. And we're taking that area and breaking it up into a bunch of little chunks, a bunch of little dx dy's, d areas. Okay. So we put our bounds on the integral. Y is going from 1 to 2. And x is going from 0 to 3. And I paused there because I was checking my integral and making sure that I had written it correctly, and I had a moment, and everything's fine. X goes from 0 to 3, and that's why I drew the picture, because then I had a reminder of what's going on here. Once you have written the integral with the bounds in the correct place, the hardest part is almost done. And then you integrate your function with respect to x. While you are integrating with respect to one variable, the other variables are constant. And the way that this is represented on the diagram is it's like we're scanning the x back and forth. So we integrate x on this line, and then we integrate x on that line, and then we integrate x on that line, and so on and so on. And on each of those lines, y is a constant. So that's what's happening here geometrically. You do the integral. I picked an exponential so it'd be easy. Remember chain rule. And then we put in the bounds of integration, and those are the bounds of x. So that will remove the variable x from the expression. This is one of the ways you know you're doing your integrals correctly, is if variables start disappearing as you go through the calculations, because you're putting in those bounds to put in values for those variables. After getting rid of the x's, then we are down to a single integral, just integrating over y, and then we get an answer. Maybe we'll get an answer. Oh, okay, we're going to keep going with this one. So here's our expression, and we put in the bounds for y, and you're like, okay, so I get e to the 12 or something. Feed it to the computer at this point. We'll be doing some stuff by hand. We'll be doing some stuff numerically. The answer happens to be about 7,500, 7,400. But if you were doing this by hand and you just had paper, then, you would leave it in simplified form after putting in the numbers. Okay, I want to get straight to why this stuff matters. One really big place where multiple integrals show up is in probability calculations. And this is more than just a quantum mechanics thing. I mean, yeah, it's a quantum mechanics thing, but all over statistics as well. This idea of probability distributions, that of continuous functions that represent the probability of some event as a causal variable changes, that is a critical concept in statistical thinking. And when you have continuous distributions, that means you can't just sum probabilities, rather you have to integrate probabilities. So what you do is you look at the probability per unit of your variable. If it's a spatial probability, maybe that's a unit volume. If we're looking at like population statistics and we're saying, what is the probability that something happens as a function of age, like the age of people, then you would have some distribution of values where you're like, I don't know, here is the probability of earning at a certain income level as a function of age. And then you have the distribution that looks something like that. And you can say, okay, what is the total probability within some range? You integrate this function of the probability density. And this is where we look at the units again, because if it's like, oh, there's a 65% chance of making, I don't know, 6 figures, then that is going to come from the probability per age group multiplied by the age range, essentially, looking at the units that is involved here. When we are doing probability calculations, there is another integral that is going to always show up, and that is that the total probability must be 1. So this is not pressure and volume. This is just probability, and whatever variable is our variable. Sorry if anyone's triggered from thermo here. But the idea is that if we integrate over every possible value of the variable, then the total probability must be 1 because some result is guaranteed to happen. All right. So with that out of the way, let me talk about a physical example that is very tied to materials. And I actually want to look at materials for computing. So not the computational science of calculating things about materials, but rather the hardware architecture that we implement these calculations on. It's all built on transistors. And in transistors, I'm not going to like just do a surprise lithography lecture here, but when we make transistors, usually we are etching silicon with ultraviolet light at very small wavelengths. And we're getting now to the point where the processes involved, like the photolithography and the etching processes, create features in the silicon that are single digit nanometers in size. It's absolutely wild. So, for the simplest example, like what if you just have two parallel wires on your circuit board? Well, or better yet, what if you have transistor A and transistor B, and these are transistors in some logic element that is going to be doing math on your signal, for example? Well, as electrons are in wire 1 and as electrons are in wire 2, these electrons, being quantum mechanical creatures, they are going to have a wave function that gives a probability distribution for their location. And it should be centered on the wire and it should be mostly contained within the wire, but everything is fuzzy in the quantum world. So our wave function for the electrons on the wire might look something like that, where so implicitly there is a probability axis here, and then there is a distance axis horizontally. And the majority of the probability density of this electron is concentrated in transistor A, or transistor 1 as it should be. But there is this tail. There's some non-zero probability that the electron may be detected out here. So what we need to know is, what is the probability that the electron actually ends up appearing in wire 2 or in transistor 2, which is not where it's supposed to be? This is a cause of errors in calculations. So not like numerical error stuff that we've talked about with the programming, but physical errors of switches getting tripped at the wrong time because the electrons quantum mechanically tunnel from one conductor to another instead of going through the gates that they're supposed to. This is actually one of the design criteria that is involved in circuit board design, is understanding these leakage currents and being able to plan for that in your error correction algorithms. So anyway, the probability that the electron tunnels over to the second transistor from the first one is given by a multiple integral. It's an integral over the volume of that transistor of the, in this case, the square of the absolute square, hello complex numbers, of the wave function of the electron. And so you have to say like, oh, this is some kind of Gaussian thing. So this is some sort of like e to the minus x squared-ish business. And then you integrate that thing. And then you say, ha ha ha, I know better than you. E to the minus x squared doesn't have an integral. And that's where I say, ha ha ha, I know better than you. It doesn't have an analytic antiderivative, but you absolutely can integrate this function if you have a definite integral, which you do have a definite integral. There are some bounds on the size of the transistor. Sorry about the spurious dx there. I just got habits, integral of stuff dx. So the point is that this function, this probability density function, has some non-zero value in the volume region that is contained in the second transistor. And so you have to integrate over that volume to see what is the probability that the electron pops up over there. So that's one place where this kind of thing occurs. The other really big concept, physical concept I want to get across today, one concept was really just the order of integration, keeping track of your bounds, that stuff. And then this is the really big one physically, is this idea of flux. This is something that is very important in kinetics for sure, but also shows up in a lot of areas. It shows up in mechanics when we talk about energy flux through surfaces. It shows up in thermodynamics when we're talking about heat fluxes. It is going to show up in electricity and magnetism when we think about things like electric field fluxes in conductors. It's a very, very recurring topic. And the flux at the end of the day is this way of quantifying how much of something flows through a given area over time. And that shows up very directly in the units. It's going to have units of something, where the something is dependent on which physical quantity we're discussing, heat or electric fields or light or particles or whatever. And it's per meter squared per second. And this is our area and time idea. And the flux calculation that we do is then going to involve doing an integral, a multiple integral over some surface area if you want to know the total amount of substance, we'll say, that goes through that area. One place where this shows up, as I've had here on the bottom, is in Fick's diffusion equation. This is a flux equation. This J thing, this is a flux of particles. That's partly what the vector is showing, is that it's movement in a direction. The particles are going somewhere. They're going in a certain way. And that way is given by, hello, friend, gradient. You've been lurking down there. Good of you to show up so soon. It's the gradient of the concentration determines the flux of particles. So what's happening here is you would say, okay, I know my concentration scalar function. I know how much concentration is at each place in my region that I'm studying. Based on those differences in concentration, there will be directions where the change of concentration is the greatest. And that direction of greatest concentration change leads to flow of particles because they want to go from more concentrated to less concentrated areas. And so we have this direct proportionality between the gradient of the concentration telling us the direction where concentration changes the fastest. That tells us the direction of the flux at that location. Particles are going to go to where they can, as quickly as possible, decrease the concentration where they are. And that's this J vector, is that flux of particles. So then if you wanted to know how many particles flowed through a membrane, for example, then you would integrate this flux function over the area of that membrane, and then that would give you a flow rate of particles per time. Okay, I know I was a little back and forth there. I hope that, I won't pretend it 100% made sense, but I hope you got something good out of that. If not, give me questions in the check-ins. All right, there's a second example I'll also give, which is when quantities are non-uniform in space. If you have, like in the case of materials, imagine you have a composite that has different densities in different regions. Like if it's a layered composite and these different layers have different densities, maybe there's even some density gradient at the interface, then to know the total mass of the object, you have to integrate that density function over the volume of the composite. That's not what I'm talking about here. It just popped into my head and I'm like, oh, what a cool example. But when we look at wires, speaking of electricity and magnetism stuff, which really is quite important in a lot of material applications, there's electric fields everywhere in the environment. Materials interact with them. So you have a cross section of a wire here. And in Physics 240, you often pretend that the wire is just sort of uniform and like there's just current in the wire. Well, it's not that simple, because if you try to put this current in the wire, the electrons are trying to get away from each other. They're all negatively charged and they are having this repulsive interaction. So what you may often find is that the density of electrons at the surface of the wire is different than the density of the electrons inside the volume of the wire. And then you're like, okay, but what is my total current? Well, my total current is found by integrating the density of the current. So the current density is what it's called, fancy that. So my total current is given by integrating my current density, which is often given by little j, over the cross-sectional area of the wire. So you have that density distribution. Maybe it's more concentrated on the edge, gets less in the center, and then that integral gives you the total current. But even better than that, you can be like, okay, what's my total charge that flows through the wire in a certain amount of time? Well, that is going to be the time integral. Since current is charge per time, I can integrate my current with respect to time to find the total charge flow. And so now this is implicitly like a very multi-dimensional integral because it's the integral dt of the integral over the area of the actual current density in the wire. And so these sorts of chains of integration can let you go from one quantity to another, to another, to another. And then if I give you a really hard problem, I'm like, so what's the magnetic field in the wire? But we won't go there yet. Will we get there? I honestly don't know. Maybe not. But I do feel like electricity and magnetism stuff is a really good application of a lot of these vector calculus concepts. And it is something that's materials relevant. So bonus. Okay, that was my 20-minute summary of multiple integrals. There are certainly things that I did not cover here that are important in some cases, like these different integral theorems, Stokes' theorem, Gauss's theorem. I mean, those are important, but you can only do so much in one day. And I wanted to focus on the basics and get into this idea of flux because that is such a critical concept to understand, not only in kinetics, but in many fields. And now that we have our tools assembled, we have ordinary differential equations, we have matrix methods, we have multivariable calculus, we get to put it all together and do partial differential equations. This really is the main goal of this course. It's exciting. This is the math that we use to understand how the universe around us changes over space and time. I mean, you kind of can't get bigger picture than that. It's very exciting. It can be hard. I will admit that. The challenges are not negligible. So, if you're a little worried, that's okay. It's going to be okay. We will get through this together. I'm here to help. I believe in you. You can do the thing. Probably. All right. Well, enough playing around. This is where we're going. We get to see all the pieces come together. It is a good time. So please look forward to it. And with that, I'm going to call it a day. This is the only video for today. We are going to start with the differential equations work next time, and that's a little more involved, so we're saving some time for that. See you there.